time. We're going to have an addendum here of a couple things that need to be said, but that I neglected. Well, not neglected. I would have said, then we just ran out of time. So the first, we have been talking for a while about how valence electrons. Oh, well, let's title this first. Let's call it properties of elements continued. Properties of elements continued. What, Gunnar?
Why can't you just
What? Conted. You can if you want. Yeah, you can abbreviate. People oftentimes do abbreviate continued. C-O-N-T apostrophe D. You can do that if you want. I didn't, though. Properties of elements continued. We've been talking for a while about valence electrons and how important they are, but why are they important? We say that valence electrons are the most important electrons for chemistry, because what is chemistry?
elements reactions?
Yeah, it's to do with, chemistry is the study of elements and their reactions, which we abbreviate RXN, little s, if it's plural. RXN means reaction. I think we've shared this before. But chemical reaction forms, or as chemical reaction occurs when bonds break and form. And it has to do with chemical bonding, which we have talked about before. The valence electrons are those that are used in bonding. Valence electrons are those that are used in bonding. There are three main kinds of bonds, and there are categories within these, but the three main kind of bonds that we're going to talk about, and this is mostly in chapter 20, but we get a little head start here just so that because chapter 20 is pretty dense with stuff we need to do, so I usually, and it's on the test, start talking about bonding in this chapter so you have some heads up. The three kinds of bonding that we talk about are metallic, covalent, can you read these okay? And ionic, or is this too small? Metallic, covalent, and ionic. I asked you a question.
I can read it perfectly.
Okay. I'm going to change colors here. Ionic. I-O-N-I-C. Hey, can you tell me what of the kind of elements that we have on the periodic table, what kinds are probably involved in metallic bonding? Metals. So this is the bonding of metals to other metals. Let's say the bonding of metal atoms to other metal atoms, because this happens within a metal. So it isn't, but if we assume this table right here is made of solid iron, the iron nuclei, why did he write Fe in these circles? What are those supposed to be? Iron nuclei. These are supposed to be iron nuclei. The iron nuclei are all, it's like, I've often described this as like a hippie commune, where they're all separate things, these nuclei, but they all share everything. They're all sharing in a hippie commune, people who are separate people, all share housing and their food and whatever automobiles they have and their wives or husbands and their responsibilities. They share all these things. And in the same way, these iron nuclei share all their electrons. So the electrons just kind of float around all the different nuclei. And this model is called the sea, like the ocean, of electrons. Because the electrons can flow between the others. And that's what gives them a lot of their properties. Let's think about, remember, metals are malleable, aren't they? A single metal atom is not really malleable, but if you have a lot of metal atoms, like the table leg, and you hit it with a hammer, maybe these three got hit by a hammer, and so they all shift down, but they're still bound there by the sea of electrons. So they move and they stay where they have moved to. That's what malleable is, right? The atoms move and they stay where they are. That's like when you dent a car, the metal moves, and then it stays there. That's what malleable means, right? And that's because of the sea of electrons. How might the sea of electrons relate to their electrical conductivity? Do you remember what electricity was defined as? Electricity is the flow of electrons. Do you see how this might relate to that? If we have a charge over here, the charge can easily flow through this metal because of the electrons. The electrons flow easily. That's the definition of a metallic bond. What kind of elements are engaged in a metallic bond? Very easy, metals. In a covalent bond, let's switch actually. I'm going to do ionic first. No, I'm not. I'm going to do covalent first.
Do it in brown.
Do it in brown, yeah. Let's do it in brown. This is bonding between metals and, guess, nonmetals. And that's not even right. Bonding between, please erase that. Bonding between, and forget that I said it, two or more nonmetals. I got confused because I was going to switch these and I didn't. Two or more nonmetals. Bonding between two or more nonmetals. So we have, for instance, give me an example of a nonmetal from the board there. Boron. No, boron's a metalloid. Okay, let's not use the noble gases because they don't bond. That's, yeah, carbon. We'll say carbon and oxygen. So we have one carbon atom and two oxygen atoms. And they're stuck together by what? Break down the word covalent. What's that probably mean?
Covalent.
What's the co mean?
Together.
Together. And valent probably referring to
Electrons.
valence electrons. So they're sharing valence electrons. They're sharing valence electrons. Who are sharing valence electrons? Nonmetals. Two or more nonmetals are sharing valence electrons. The valence electrons are spending time both with the carbon and the oxygen that bonds them together. Sharing. A covalent bond? What verb? No. That was a question, not a beginning of a sentence. What happens to the covalent bond? Question mark. What verb? They share. They share. And then we'll do this one in orange. Go Rams. This is bonding. This is ionic, and it's bonding between a metal, what we call cation, and a nonmetal, what we call anion. You know probably, if you know anything about batteries, you know that batteries have a cathode and an anode. Those are nodes, positive cathode, negative anode. Then this one, we have a metal positive
With a Mitchell node.
cation and a nonmetal negative anion. Why would the nonmetals be negative? How many valence electrons do they often have?
Valence?
Yeah.
6.
6, 7, 8, etc. Or not 8, but, well, I mean, nonmetals do. But 5, 6, or 7. How do these want to get to 8? If they have 5, 6, or 7 valence electrons, what do they want to do with electrons to get to 8? Get more. And since electrons have a negative charge, if they get more electrons, they have a negative charge. So the nonmetals are called anions because they have a negative charge, and the metals, because they want to give up electrons, form a positive charge, and that's called a cation. So what holds them together, dog? Well, if we have, for instance, in your very, very common table salt, here's sodium. Should have been not green, probably. Here's chlorine. What does sodium want to do to get to a stable 8? Look at where he is. No. Look at this. How many valence electrons? 1. What's he want to do to get to a stable 8?
Add a 7.
No.
Add.
You just told me. Lose 1. So if it loses, but listen, the electron can't just go. Just like your parents, they desperately want.
Just go.
Your parents desperately want you not to be in their house anymore. I know you. I know many of your parents. Your parents want you gone. But they can't just say, leave now and never come back. What they have to do is they have to wait. They have to wait until you can go to college or until you get a job or until you get married. And then they can say, now that you have somewhere else to go, just leave. It's the same way. The sodium wants to get rid of its valence electron, but it can't just get rid of it. It has to have somewhere to go. Where can the sodium's 1 electron go? Chlorine. The chlorine wants it because the chlorine wants 1 more electron. So now, sorry, that's the negative charge, forgive me. So now the chlorine has 1 more electron and it has a negative charge. The sodium has lost an electron, so it has a positive charge. What's true of negative and positive charges, babies? They attract. So there's an electromagnetic attraction here that holds them together and forms, now instead of sodium and chlorine, we have a compound, sodium chloride, which is table salt. These are the 3 kinds of bonding. Metallic, which is between metals, covalent, which is between a metal and a nonmetal, and I said it again. Covalent, which is between 2 or more nonmetals, and ionic, which is between a metal and a nonmetal. Do you have questions about those 3 things? Now let me tell you another thing. sometimes, let's say we have, instead of sodium there, we have calcium. I'm going to draw this one bigger. We have calcium. How many valence electrons does calcium have? Look at the periodic table. It has 2 valence electrons. So what if we what if we put the calcium in the presence of chlorine, just like this? How many does chlorine want? How many valence electrons does chlorine want? It only wants 1. So what's going to happen? Chlorine can only take 1 valence electron. So will calcium give it 2? No. It only wants 1. So calcium is going to give it 1. So now the chlorine has a negative charge. The calcium now has a positive 1 charge. But what else has to happen?
They get bonded together.
Okay, they do get bonded together, but the calcium still has 1 valence electron it wants to get rid of. Where's it going to go?
Into space.
No. Can't. No. Can't. Give it to another. Give it to another chlorine. Just like some of you cowboys are only happy if you got a chick and a side chick. It takes 2 people to make you happy. That's true, and that's gender neutral. That could be a girl too. That's true of calcium. Calcium needs to have 2 chlorines. Calcium needs to have 2 chlorines. For instance, calcium needs to have 2 halogens to make it satisfied, to make it fulfill the octet. So we end up with, instead of CaCl, this was NaCl. We end up with now CaCl2 because the calcium has a 2 plus charge. What if, last example, and then we're done for the day, what if we have calcium and, let me do a different color because I always used that one for chlorine, calcium and oxygen. Well, how many valence electrons does oxygen have?
6.
So how many valence electrons does it want to gain?
2.
2. And calcium has 2, and so now the calcium just gives both of them to oxygen because oxygen will take 2. And we end up with not CaCl2, but CaO. And that's it, because there's just 1 O. So the number that bond with it tell you what its charge is. Does that make sense?
Yes,
That will become very important in the next chapter. There is, listen, before, we don't have time to talk about it, but there is a vocab word called diatomic elements. Do you have that in your vocab list? You need to know that for the test. We will talk about it in person tomorrow, but we need to know about diatomic elements for the test. Bye.